Hi there and welcome. This video is on section 6.4 and 6.5, the main learning objectives, the things I would like you to be able to do after completing 6.4 and 6.5 are to explain the implications of the central limit theorem of statistics for sampling distributions. Secondly, to be able to use a QQ plot to determine if a data set is from a normal distribution. And lastly, to be able to find probabilities using a sampling distribution. So I'm going to start off by just doing a short review of what a sampling distribution is. I covered this in the previous video if you want to check that one out. But briefly, um, a sampling distribution, right here, I'm starting right here, is created from an already existing distribution. So you have to have a set of data somehow. It's usually given to you, and you're going to be from the set of data creating a new set of data, a new distribution. Okay, so how do we do this? Well, we're going to do this by taking repeated samples of size n from that already existing distribution. Each sample, remember, of size n, is used to create a single data point for our new sampling distribution by calculating the mean of that sample. You can actually calculate the variance or proportion of those samples, but primarily we're going to be calculating the mean of each of those samples. So here's just a short, simple example. So suppose that we know that a population of adult females have resting heart rates that are approximately normal distribution with a mean of 80 beats per minute. Whoops. Mean of 80 beats per minute and a standard deviation of 10 beats per minute. So we have this bunch of people. We know generally the population mean is 80 and the population standard deviation is 10. All right, so from this group, we take a simple random sample of 25 people, it would be 25 adult females, and we measure each woman's resting heart rate. So now we have 25 sort of data points from our big population. We take these 25 data points, these 25 heart rates, we add them together and divide by 25. That's how you find the mean. You add stuff up, divide by how many there are. So you take these 25 readings, add them up, divide by 25, and find the mean heart rate for the sample of 25 women. This mean is a single data point for our sampling distribution. So that's 1 point for our new sampling distribution. Now we take another simple random sample of 25 adult females and measure each woman's resting heart rate, and again, find the mean of this new 25 people. The mean is our second data point. So we have the mean from the first group of 25, we have a mean from the second group of 25. Each of those means is called a data point in our sampling distribution. And we keep repeating this process to gather as many data points as we wish. So the sampling distribution is made up of means of an already existing distribution. We have to set a sample size. So in this case, we're saying the sampling distribution is the means of 25 women at a time. So that creates this new distribution where each data point is a mean. Hopefully that explanation, that summary makes sense. All right, so what do we know about the sampling distribution? Well, we have this thing called the central limit theorem. It was discovered around the 19th century. It was kind of updated in the 20th century. In any case, the central limit theorem shows that if you have a large enough sample size n, three things happen. The sampling distribution will be normally distributed. Having a normal distribution is really important because most of our formulas only work for normal distributions. So having a knowledge that our sampling distribution is normally distributed is great for being able to do all our calculations. Next, the central limit theorem says that the mean of this new sampling distribution, it's usually denoted as X bar, but sometimes my little bar doesn't translate over to a PDF. So it should say X bar there. So the mean of the sample distribution X bar will be approximately equal to the same original mean of the distribution. This is the mean of the original distribution. Lastly, the standard deviation of our new sampling distribution, which is usually denoted as S, will be approximately equal to sigma divided by square root of n. If you remember, sigma is the standard deviation of the original distribution. So we have this new distribution, which is normal, has a known mean and a known standard deviation. Perfect for doing all of our calculations we need to do for our statistics problems. Surprisingly, with an n bigger than 30, we actually kind of guarantee all three of these results. So when we talk about a large enough sample size of n, we typically are talking about bigger than 30, which isn't very much when we're doing a bunch of statistics. Finding 30 data points isn't typically that challenging. However, if the original distribution is already normally distributed, we can actually use smaller numbers than 30, much smaller numbers than 30. So a sampling distribution is very convenient, and we either need a sampling size greater than 30, or we need to know that the original distribution is normally distributed. So that's kind of a little summary I have over here, right? We're going to be creating a sampling distribution, and we need to know the original distribution is normal, or we just need to choose a sample size bigger than 30. All right, so we'll do one more thing related to this, and then we'll do some examples about sampling distributions that will help you see what's going on. So the second thing, the second learning objective is about QQ plots. So let me talk about that. So here we have the second learning objective, to use a QQ plot to determine if a data set is from a normal distribution. So this is essentially a quick and easy way to know if our original distribution is normal or not. Remember, we need to have a sample size bigger than 30, or we need to know that the original distribution is normally distributed. So how can we determine if the original distribution is normally distributed? Well, sometimes we're just told in the instructions saying this is a normal distribution. So kind of it just tells us and we're done. We actually have done the exploration previously. We've done this by creating a histogram of data to visually check if it follows a normal distribution. So if you remember creating histograms, if they had like a symmetric thing where they kind of went up like this and then back down like this, we said, oh, that looks like a normal distribution, because like the tops, which is where the height of the frequency, right? The frequency is up here. So the frequencies went up and back down like this. And we say, oh, okay, that's a normal distribution. We have another way, ostensibly easier, according to the statisticians, to determine if a data set is normally distributed. And that's called a quantile plot, or abbreviated as a QQ plot. So QQ plots, they plot the data points along with the corresponding quantile of each data point. And if the QQ plot follows a straight line, we can determine that the original distribution is normally distributed. So that's a lot of word salad there. Let me show you an example of what's going on here. So I went to StatCrunch and I just pulled up an example. Let me zoom in a little bit there so you can see more stuff. Or I can zoom out, sorry. So I went to StatCrunch and I pulled up a data set. I found a data set for the amount of sugar in 35 grams of each of the most common breakfast cereals. They chose 35 grams because that's about a serving size for a lot of cereals, but they standardized it for every cereal. So 35 grams, how much sugar is in each of the most common breakfast cereals? And they made a QQ plot. I made a QQ plot on StatCrunch and I pasted it here. Just to remind you, in StatCrunch, you just go to graph and you can make a QQ plot right here. It's just one of the options in StatCrunch. You don't really have to do much more than just ask it to create a QQ plot for you. And I did so. And this is what it looks like for my data set. I don't want to show you all the numbers. It's not important for this lecture here, but I graphed all these data points on a QQ plot, and this is what it looks like. The thing is, if the data points sort of form a straight line, or at least close to a straight line, then we know the original data that the QQ plot came from is actually normally distributed. So this is what the plot looks like. This is a common looking kind of plot, where the dots don't exactly follow a straight line, but there's a lot of dots. And generally they're close to, they're reasonably close to a straight line. There's a few that are above, a few that are below, but that line kind of shows the direction of all the dots, and there's no like deviation from that line. They kind of all cluster around the line. There's no like obvious pattern that it's following other than that. Like if it wiggles back and forth, let's suppose that um my plot kind of went like this, like a very clear wavy thing. Even though it's like some above and some below, we wouldn't consider that following a straight line because it follows a different pattern. So the example we have here is it follows like the straight line pattern. Whoops, there we go. There's no other pattern it follows. And so we say this data of the amount of sugar in 35 grams of these breakfast cereals is normally distributed. So part of the homework, you'll be practicing making QQ plots and then trying to develop sort of a repertoire of how to identify which ones follow reasonably close to a straight line and which ones do not. Generally, the more data points you have, the easier it's going to be to tell whether it follows a straight line. And with very few data points, it's going to be harder to tell that it follows a straight line. So kind of keep that in mind when you're building up your intuition, your experience with calling these out. All right, so that's the QQ plot thing. It helps you determine if the original distribution is normally distributed or not. All right, let's do some examples. Finding probabilities of a sampling distribution. We have found probabilities of other kinds of distributions. They have to be normal for us to use our traditional formulas. So we're going to kind of use a sampling distribution because we kind of know that it's going to be normal as long as we have one of those two conditions. Either the original population is normally distributed or we have a sample size bigger than 30. All right, so we're going back to my first example of these women's resting heart rates. We know that it has a mean of 80 beats per minute and a standard deviation of 10 beats per minute. So we are going to consider the sampling distribution of this data set, of this distribution, using a sample size of 25. What is the approximate mean and standard deviation of the sampling distribution? Well, according to the central limit theorem, CLT, we know that the sampling distribution has a mean x bar equal to mu, where mu is the mean of the population, and it has a standard deviation. I wanted to put them on top of each other. Let me kind of fix this a little bit so that it fits. X bar is equal to mu, and the other formula was on there that the standard deviation is equal to the original standard deviation, the standard deviation of the bigger distribution, the original distribution, divided by square root of n. All right, so in our case, the mu, the mean of the original distribution is the 80 beats per minute. And the standard deviation of our sampling distribution is equal to the standard deviation of our original distribution, which is a 10, divided by the square root of the sample size. The square root of the sample size is 25. So it would be 10 divided by square root of 25. We could do the math there. You can grab a calculator. I actually know the square root of 25 is 5, because 5 times 5 is 25. And so that's supposed to be a 5 down there. And so I know that 10 divided by 5 is equal to 2. And so we have the standard deviation of this new sampling distribution is 2. So once we have a normal distribution, which we know the sampling distribution is a normal distribution because the original distribution is normal. Remember, if the original distribution is normal, that guarantees that the sampling distribution is normal as well. So we have a normal distribution, we have a known mean, and we have a known standard deviation. So we can just pull up our normal calculator and calculate the proportion of the data in the sampling distribution that has any particular characteristic. For example, suppose I want to know the proportion of the sampling distribution which has values greater than 85. Okay, so I go over to my StatCrunch. I'm going to go to my calculator, and I know it's normal, so I'm going to go to my normal calculator here, and shows me my standard normal, but I need to make the mean and standard deviation match. My mean is 80. Oops. There we go. My mean is 80. And just to recall, the original distribution had a standard deviation of 10, but we are looking at the sampling distribution. The sampling distribution has a standard deviation of 2, right? So it's not the same as the standard deviation originally. It's a smaller standard deviation, right? Smaller. So I'm going to put in a 2 there because this question B that we're working on right now is talking about what proportion of the sampling distribution has values greater than 85. So when I go over here to my StatCrunch, I'm going to put a standard deviation of 2, right? That's for our sampling distribution. I want to find out the values that are greater than 85. And I'll compute. And it looks, here's my distribution, my sampling distribution. It has a mean of 80, has a standard deviation of 2, right? And then 85 is over here. So the proportion of people, proportion of the means of 25 people, the proportion of these data points in the sampling distribution is very small. It's only this. So there's very few times when I take a mean of 25 women that their mean, their average will be larger than 85. How often will that happen? 0.006, which is about 0.6% of the time. So 0.006 or 6% of the time. So I'll go over here. What proportion are greater than 85? 0.006, which is approximately equal to 0.006, which is equal to 0.6%. So very, very few times when I create a data point for the sampling distribution, in other words, I gather 25 people together and women, I measure their resting heart rates, and I find the mean, very few times this will be larger than 85. Okay, let's now switch to the original distribution and find out what proportion of the original distribution has values also greater than 85. So same kind of greater than 85, but the original distribution. So what's different about the original distribution? Well, it has the same mean, but it has a different standard deviation. The original distribution has a standard deviation of 10 with the same mean of 80. So let me go back to my StatCrunch. I'm going to do my 80 mean, but I'm going to go back to my original standard deviation of 10, and I'll compute again for greater than 85. So here's my original original distribution with a mean value of 80. And then if I go out 10, I'm jumping by tens each time. So that's 1 standard deviation, 2 standard deviations below, 1 standard deviation, 2 standard deviations above. And 85 is like right here between 80 and 90. It's like a half a distribution, half of a standard deviation away from 80. You can see the area here, the data, the proportion is much larger. In fact, it's a 0.308 or almost a 31%. So I'm going to go back and write that in there and my little lecture thing. Right. So you can see that if I look at the original distribution, which is just one person at a time, and try to see what is the proportion of the data points that I'll look at that have a value greater than 85, the answer is almost a third, 30.8%. But if I look at the sampling distribution, which is the mean of 25 women at a time, the chance that they, as a group, will have a mean greater than 85 is less than 1%, 0.6%. So why are these so different, right? So part D says, explain why the results for, whoops, it's supposed to be B and C. I guess I changed the lettering at some point and never updated it. So this is supposed to be B and C, the previous two, right? Explain why the results for B and C are so different. And I'm going to help you see that by giving you a little visual on Desmos, because I think visually it's easier to see than for me just to try to explain it. So I have here on Desmos, I already prepared some graphs to show you. This is the original distribution. You can see that the mean is 80 and 10, 10. It goes by tens because that's the standard deviation of our original distribution. I marked off two standard deviations. So this is two standard deviations below and two standard deviations above. So the proportion, the data here is 95% of the data. Remember this 68, 95, 99.7% empirical rule. We know if we go two standard deviations above and below, that's 95% of the data. So 95% of the data is there. So that's like most of the data within 60 to 100. So let me show you the distribution, same middle, same mean of 80, but now a standard deviation of 2. Before I had 80 with a standard deviation of 10, and now I have 80 with standard deviation of 2. This is how you type it into Desmos if you want to do it yourself. So I'm going to show this. Oh, and this now I put in green looks very different. Like it goes off the top of the screen. Let me zoom out a little bit so you can see it. It does actually stop right up there. Okay, so one thing to notice is that the data is really squished down close to 80. Why is it so tall? Why does it peak up like this? Well, remember, we're talking about a frequency distribution here. We're talking about a standard, description of our distribution. So we have the same amount of data, right? We have the same amount of data we're comparing for the original distribution and the sampling distribution, right? And so we need more data packed into a smaller spot. So just like our histograms, if you have more data, the box gets higher and higher. So in this case, if you have more data close to 80, it'll just go higher and higher and higher. The frequency will go higher and higher and higher. Like it's like 20% at the peak right here of the data is all like right near 80, right? So it just smooshed in together. And so you can see that when you take an average of 25 at a time, the data gets very compressed and close to the mean, as opposed to when you just take one at a time, the data is more spread out. And that may intuitively make sense if you think about the fact that when you take these measurements, these 25 women at a time, and you average them together to get a mean, right? So some people may have higher standing heart rates, some people may have low standing heart rates, but when you have a bunch of 25 of them, the ones above and ones below are going to kind of balance each other out, and the average will be close to the middle. Whereas if you take one at a time, sometimes you get somebody that's high, sometimes you get someone's low, sometimes you get people in the middle, but there's nothing to add together to average out. There's no balancing of that. So we get the balancing or the averaging out with the sampling distribution, which makes all the data smushed together near the middle. Okay, so let's go back to our original distribution here. I can graph the place where it's 85 and above. So here's the 85 and above, just like we showed before on StatCrunch. And you can see that, it's all of this stuff right here. And then if I do the same thing for my, sampling distribution, I'm going to squeeze it down a little bit so it's easier to see. And I again do the 85 and above. You can see that 85 and above is just this little sliver right here, a very small proportion. And if we put it all together, Let's get rid of this, bring back this, rescale it, put in this, zoom out a little bit so you can see the bigger picture. And then, so this guy right here is the original distribution, 85 and above. And this guy here is the sampling distribution, and 85 and above is just this little smidgen in here, right? I mean, it goes all the way, but since the graph goes to the axis, basically, then it's adding in the 0 data points as you go far. There's no one out here where there's an average of 25 and the average is 120 or 100, right? We have the averages kind of, or at least 99.7% of them are within three standard deviations. And if you go 4 or 5 or 6 standard deviations, you're basically getting every single possibility in there. So visually, this hopefully will help you understand the difference between a sampling distribution and a regular distribution, where everything gets compacted and we get a much smaller standard deviation. Remember, it's divided by square root of n, so divided by a number gets smaller. And therefore, you have this idea of these means are much more closely centered to the middle, and you get a different probability that we calculated in this example. All right, let's finish off our lecture for today. So my explanation was verbal, showing you the pictures. I don't want to write all that stuff, but hopefully the explanation and the pictures can help you understand the answer for D. And my last question here is, what would we need to change about our sampling distribution if we suspected that the original distribution was skewed to the right? All right, so suppose we have the same situation with these resting heart rates, but we didn't know it was normally distributed. Normal distribution is kind of nice, but suppose we actually think that the distribution was skewed to the right. Skewed to the right is not a normal distribution. It means the tail goes off to the right, so it's no longer symmetric. It's got more stuff to the right. So what do we do now if we want to do our calculations, our sampling distribution, but the original distribution is skewed to the right? So the answer is, it doesn't matter how the original distribution is skewed or not skewed. It could be uniform. It could be anything. It doesn't really matter as long as we choose, wait for it, n bigger than 30. So originally we took 25 people at a time and averaged those measurements together. We found the mean of a sample size of 25. If we suspect that the original distribution is not normal, anything but normal, then we just choose n to be bigger than 30. Choose 35 people to measure and then find the mean of. 25 wouldn't be big enough, right? That would, of course, change some of our calculations in terms of our standard deviation. We'd be doing 10 divided by the square root of 35 if we did choose a sample size of 35. But that's our options. Either know that our original distribution is normal, or just choose an n value bigger than 30 when doing your computations for the sampling distribution. Okay, so that is sort of the end of our video. And just to recall, the big ideas I was trying to get at here were to explain the implications of the central limit theorem for sampling distributions, to be able to use a QQ plot to determine if a data set is normal, and also to find probabilities using a sampling distribution. If you have any questions or need some more examples or have any what-if scenarios, please don't hesitate to reach out. And I hope you have a very nice, wonderful day. See you in the next video.